Hello everyone, I am from Huazhong University of Science and Technology, and today I will present our work QKSAN, which concentrates on building multiple sanitizers for fuzzing in vehicle commercial off-the-shelf OS kernels. As car becomes increasingly intelligent, the code within components like IVI and ECUs has grown more and more complex, and these components are now equipped with operating systems such as Android, Linux, QNX, and FreeRTOS. However, in-vehicle kernels are often closed source or use highly customized Linux kernel, making it difficult to find bugs in them. For example, QNX, a widely used commercial OS in vehicles, has very few CVEs reported in recent years. Then why do we need QKSAN? For user space programs and the Linux kernel, we already have virtual fuzzing solutions such as AFL++ or Syscaller. However, these solutions cannot be directly applied to commercial off-the-shelf kernels due to the lack of fuzzing oracles. For example, there is currently no ASAN implementation for the QNX kernel, making it difficult to detect memory safety violations during fuzzing. So, what are the challenges in building QKSAN? First, due to the closed ecosystem of in-vehicle kernels, we cannot obtain the source code. Therefore, the compile time instrumentation-based technologies such as ASAN and KSAN are infeasible. Then we may consider using a hypervisor-based method like QMIL for instrumentation. However, for system-level softwares, such an approach often introduces significant performance overhead. Furthermore, existing sanitizer implementations do not support enabling both ASAN and MSAN simultaneously. Let's take a look at the design of QKSAN. To meet the requirements of sanitizers, QKSAN needs to monitor the state of the memory allocation inside the kernel. So QKSAN firstly takes a list of target functions related to memory allocation as input. It runs the kernel in QMIL's TCG mode and traces the start and the end of the functions. Then it uses a special shared memory to record the states of the memory allocation, which enabling both ASAN and MSAN. Also, QKSAN can selectively enable sanitizers for special processes, which can reduce the performance overhead of fuzzing. The first step of QKSAN is to implement the function level tracing. First, we insert hooks according to the input target function list. When the function is called, we record the return address and stack pointer. To trace the function's end, we check if the kernel reaches the return address and the stack pointer if the stack pointer matches the one we recorded before. If so, we can regard the function has been returned. Through this way, even if the execution of the function is interrupted, we still won't miss the function's end. Then we can manipulate the shared memory accordingly. Here is a table of the traced functions, mainly including the memory and cache management functions, context switch functions, and some special ones. To enable ASAN and MSAN bothly, we design a special compound shared memory. Every 8 bytes of the kernel memory is represented by 10 bits in the shared memory. The shared memory contains 2 levels, which can easily be computed from the kernel virtual memory address. We found that 10 bits are enough to represent the memory states, including whether the memory is allocated, initialized, freezed, and or red zone. This design can help save the memory consumption of the sanitizers and allow us to enable both ASAN and MSAN. For better fuzzing performance, QKSAN can also selectively enable sanitizers for special processes. It monitors the context switching through function-level tracing, and enables the instrumentation of sanitizers only when the interesting process is running, such as the executor in the figure here. We implement QKSAN based on QML with additionally 5,000 lines of code. QKSAN takes a JSON file as a configuration, which contains necessary information for instrumentation. Here is also an example of crash reports generated by QKSAN. It successfully catches a heap buffer overflow bugs in the QNX kernel, and it contains the memory address, the type of the bug, and whether the chunk is where the chunk is allocated, just like the ASAN. But no simple information, since we are working on a closed source kernel. To fuzz the QNX kernel better, we also write some simple syscall templates for syscaller according to the QNX documents. Then we can use syscaller to fuzz the QNX kernel with QKSAN enabled, which can help us find more bugs in the kernel. We also made several engineering adaptations to syscallers, making it able to collect code coverage for the QNX kernel and process reports from QKSAN. The figure on the right shows this example. We evaluate QKSAN by reproducing real-world Linux kernel bugs and creating simple proof of concept to trigger memory violation in the QNX kernel. QKSAN is able to detect these bugs precisely, both in Linux and the QNX kernel. We also evaluate the fuzzing performance of the QKSAN. We fuzz the Linux kernel with QKSAN enabled and find 7 known bugs. For QNX kernel, we find 18 unconfirmed crashes. Unfortunately, we have not determined whether these crashes are real bugs currently. In conclusion, QKSAN is a feasible solution for fuzzing commercial off-the-shelf kernels, especially QNX, which can combine multiple sanitizers. We have demonstrated its effectiveness in detecting memory safety violations in both Linux and QNX kernel. For further works, we plan to further improve the fuzzing performance of QKSAN and provide better syscaller templates. We will also continue to find and confirm vulnerabilities in the QNX kernel. Additionally, the source code of QKSAN is available on GitHub. Thank you for your listening. If you have any questions, feel free to contact me via email.